Section 5, Chapter 8, Using the Sampling Distribution of the Sample Mean. The first two paragraphs here have been stated before in the previous section. If a population follows the normal distribution, the sample distribution of the sample mean will also follow the normal distribution. If the shape of the is known to be non-normal, but the sample contains at least 30 observations, the central limit theorem guarantees that the sampling distribution of the mean follows a normal distribution. When the population standard deviation is known, a z-statistic for the sampling distribution of the sample mean is calculated as this, using this formula for z. Let me explain what that means. Well, I already had this before. Let me delete this. We used this in the course before. When we first introduced the standard normal distribution, if a variable is normally distributed with a mean mu, then by using the formula z, and this is a standard deviation sigma, z is equal to x minus mu divided by sigma. In other words, you're calculating how far each x is from the mean divided by the standard deviation, or how many standard deviations is a value from the mean. Well, that way we convert any variable that is normally distributed to a standard normal distribution with a mu equals to 0 and sigma equals to 1. Those are the two parameters of the standard normal. And we calculated in our table an area between 0 and z. And that z can be any value, for example, 1.5. And you also saw in a previous video how these areas can be calculated using Excel. Now we have the distribution of sample means under two conditions can be normally distributed. One is the population variable is normally distributed. Second is the population shape may not be known or is not normal, but the sample size of the size of the sample is at least equal to 30. So we sample at least 30 individuals or 30 items. And then we repeat sampling many times. We will get this normal distribution, and we don't care what the population distribution look like. We will always get a normal distribution. And the standard deviation of this sampling distribution of the means, sigma x bar, is defined as sigma over the square root of n. And of course, remember, sigma is the population standard deviation. Well, we can also convert this normal distribution into a standard normal. Okay, so to avoid waste of time, we can convert it into this too by using the formula z is equal to each value, in this case is going to be x bar, minus the mean, which is again mu, divided by the standard deviation that corresponds to the sample means, which is sigma x bar. But sigma x bar is equal to sigma over the square root of n. So that is the formula shown there. And let's look at one example. The Quality Assurance Department for Cola Incorporated maintains records regarding the amount of cola in its jumbo bottle. The actual amount of cola in each bottle is critical, but varies a small amount from one bottle to the next. Cola Incorporated does not wish to underfill the bottles. On the other hand, it cannot overfill each bottle. records indicate that the amount of cola follows the normal probability distribution. So we already know that we have normal distribution in the population, so the sampling distribution of X bar will also follow normal distribution. The mean amount per bottle is 31.2 ounces, so that is the mu, and the population standard deviation is 0.4. 0.4 would be sigma. At 8 a.m. today, the quality technician randomly selected 16 bottles, and so from what we know, since the population is normally distributed, sampling only 16 bottles doesn't worry us much, because we know that sampling distribution of X bar will follow a normal distribution too. All right, so we select 16 bottles from the filling line. The mean amount of cola contained in the bottles is 31.38 ounces. So of course, as expected, the mean of a sample is going to be different than the mean of the population. Is this an unlikely result? Is it likely the process is putting too much soda in the bottles? To put it another way, is the sampling error of 0.18 ounces unusual? 0.18 is the difference between 31.38 and 31.2. Well, if we use the formula for the z value, z is equal to x bar minus mu over sigma over the square root of n. X bar, the sample mean, is 31.38. We subtract the mean of the population or the mean of the means divided by sigma 0.4 over the square root of n, the sample size, 16. If we carry this out, is equal to 1.8. 1.8 standard deviations. So in our sampling distribution of X bar, our result is 1.8 standard deviations away from the mean. So the value of 31.38 is 1.8 standard deviations away from 31.2 in the sampling distribution of X bar. And that's just one value in this infinite amount possible of results that we can obtain in the normal distribution of sample means. And this is the actual values, and here is the equivalent value in the Z distribution. Now I have a copy of the table. Let's practice the table, reading the table. The table finds areas between 0 and Z. Well, between 0 and 1.8, going down here on the Z values, 1.8 is right here. Since it doesn't have any other decimal value, so it's 1.80, we read the value right here, 0.4641. So 0.4641 is this area between 0 and 1.8, which is the same area between 31.2 and 31.38, because the population values are also normally distributed. All right, so it's 0.4641. And since all the area to the right here should be 0.5, remember symmetry, 0.5 to the right, 0.5 to the left. So 0.5 minus 0.4641 must be equal to the upper tail here, and that is 0.0359. Okay, now what do we conclude? It is unlikely, less than a 4% chance, we could select a sample of 16 observations from a normal population with a mean of 31.2 ounces and a population standard deviation of 0.4 ounces, and find the sample mean equal to or greater than 31.38 ounces. In other words, look at this distribution and this specific probability here that we found. To find something this far from the mean, it is right at the threshold of an entire probability here of 3.59%. In other words, the chances that you get something as large as 31.38 ounces or higher are 3.59%, which is a relatively small chance. we conclude the process is putting too much cola in the bottles. Now I want to review once again how to calculate this area using Excel. Remember that Excel calculates the cumulative probability or uses cumulative probability. So if we use, for example, just the norm .s.dist and type 1.8 comma true, I will find the area to the left of 1.8. In other words, I will find, if this number were 1.8, all the area to the left, all the area to the last point here. But I'm not interested in that area. I'm interested in this little area here. So since that is what I'm interested in, I should put here just simply 1, which is the entire area, minus norm.s.dist. And now I can put the 1.8 and then true. All right, so I'll be subtracting the cumulative area of 1.8 from 1. And that will give me the upper tail of the little tail. And if you notice, it's 0.0359 as we saw on the slides.